Thank you for attending our webinar today, Maximizing Throughput in Fluorescence Microscopy. I'm Kevin McCarthy, Chief Technology Officer for Dover Motion, where we specialize in high-precision stages to enable automated microscopy with high throughput. I'm joined today with a valued collaborator of many years on the optical design front.
My name is Steve Auger. I am Principal Consultant for BioDevice Partners, a design firm that's been designing fluorescence-based systems, optical systems, for the past 25 years.
First, a few housekeeping items. Our agenda is on the slide before you. If you have questions during the webinar, feel free to submit them via the chat, and we'll do our best to get to some of them at the Q&A section afterwards. In addition, we're going to avoid reading PowerPoint bullets one by one. I'm going to try for a more conversational style, and some of the slides we'll be skipping because they're a little busy, but everyone who's registered for the seminar will be getting a complete slide deck, so take it from there. When we talk about maximizing throughput in fluorescence microscopy, motion plays a key role. One of the reasons for this is that the field of view is typically considerably smaller than the sample. Common samples might include a flow cell, such as this, the standard microtiter plate, or the canonical microscope slide. The fields of view of typical microscopy systems range from about 0.3 millimeters to 3 millimeters, considerably smaller than the sample. As a result, we have to have a strategy to tile the sample and acquire all of it. There are two basic strategies to do this, and one we refer to as sequential field imaging, or SFI. In SFI, we move to a field of view, acquire the image, and then move to the next field of view, and repeat this until the entire sample is tiled. In the slide we're advancing to, you can see a flow cell where the individual fields of view, there's 10 across each lane and 218 down the lane for a total of 2,180 images per lane. There are 8 lanes, so there's a total of 17,440 fields of view here. So clearly there's an impetus to move quickly. And in this slide, the timing of sequential field imaging is described graphically. During the red portion, we're turning on the illumination and acquiring the signal. And then at the end of that period, the stage moves as rapidly as possible to the next field of view. And under that cover of darkness, with the light off, the image is downloaded to the host. This is repeated over and over again. Now, the alternative to sequential field imaging is what's called TDI, or time delay and integration scanning. And in this case, the motion is continuous at a fixed velocity down a row and then moving to the next row and repeating in the opposite direction. In this case, sample illumination, motion, and image download are continuous and happen simultaneously. In this slide, we call out the key factors for both SFI and TDI imaging. With sequential field imaging, the keys are to have very fast integration times, which means getting a lot of light on the sample and into the camera sensor, very fast motion, moving from field to field, and very fast camera downloading its image very quickly. Conversely, in TDI scanning imaging, we really want to have extremely constant velocity during the scan. We still want to maximize the fluence. In this case, we'll want to maximize the number of TDI sensor rows, and with the most modern sensors, adopt a hybrid technology where there's a read amplifier in each column. In both imaging modes, we want a sensor with both very high quantum efficiency and low read noise.
What you have in this image are the 3 basic types of microscopes, where in the earliest form of microscopes, you had an objective lens which formed an image that was then reformed onto the eye by an eyepiece. In the middle image, you see the most primitive form of a digital imaging system where you have an objective lens that forms an image directly on the digital imaging sensor. Almost all modern microscopes use what's called an infinity-corrected objective, which forms an area in the middle of the microscope where the rays are parallel or focused at infinity, and then refocused using the tube lens onto the digital imaging sensor. That infinity space allows you to insert optics that would be important for fluorescence microscopy, for example, filters or dichroic mirrors. There's a huge diversity of microscopes. For today's webinar, we're going to focus on transmissive, epi-illuminated, and epi-collected, and fluorescence-based microscopy systems.
Might point out, however, that on the super resolution column on the right, Steve was actually the designer of the very first commercial F-palm microscope.
That project was a lot of fun. The next slide shows the relationship between sensors, pixels, and field of view. A popular scientific CMOS camera has 6.5 micron pixels, 2048 of them in each direction. And if you go through a fairly typical 20x magnifying objective, what you end up with are 325 nanometer pixels down at the field of view, and which yields a field of view of 666 microns square. One of the most important and most expensive components of a microscopy system is the microscope objective. The key parameters of a microscope objective are the magnification, which is the number written on the side of the objective. However, what might not be known is that you can adjust that magnification through the use of a tube lens of a different focal length. A second key parameter of a microscope objective is the numerical aperture, which we'll cover in more detail momentarily. The third is the field number. This is what defines how large of an area or field of view that the objective is capable of. And that is basically the field number, which is written on the side of the objective frequently, divided by the objective's magnification, also written on the side of the objective. Also important to the objective is its design type, which basically is how many optical elements are inside the objective and the level of correction. Plain apochromatic objectives offer the best image quality. Lastly is the microscope objective's cover slip correction. Most biological microscopes are designed for a 0.17 millimeter thick glass cover slip. However, there are some that are adjustable up to cover slips as thick as 2 millimeters. Be aware that a mismatch between the cover slip thickness and the design thickness of the objective would induce optical aberrations such as spherical aberration.
Light has both wave and particle properties. And as a result of the wave properties of light, it is subject to diffraction. Now, the fine features in a sample that you're trying to resolve actually act like miniature gratings, and in so doing, scatter the light into a wide angle. I have here a green laser, which would normally make a single dot on the foam board, but in fact, we've added a two-dimensional diffraction grating, much like microscopy samples. And as you can see, we get quite a pattern of diffraction. And it is only by capturing those higher orders of diffraction and recombining them in the image plane that you can actually achieve high resolution. This is shown graphically in this slide, where a slit is diffracted, and we see the zero order, which is the place light would be if it were purely particles, and then we see the first, second, third, and fourth orders of the diffracted signal. And this is really part and parcel of the importance of numerical aperture.
As Kevin mentioned, in order to reconstruct an image of the highest resolution, you want to capture all of those higher orders of diffraction. And the way that you do that is by capturing a wide angle of light coming into the objective. And that parameter is known as the numerical aperture, which is basically the sine of the half angle of light collected. And you can see here that we have three different microscope objectives. The 0.1 NA captures a relatively small angle of light, so that would be lower resolution. The 40x 0.7 NA has a higher angle, and at the extreme on this figure, we have a 100x, which captures a 0.9 NA, which is a very wide angle to collect and will give you the highest resolution.
Now, it turns out you can actually go even above that, but you can only do so by introducing either water or oil, as opposed to air, between the objective and the sample, and that can get a little messy and a little complicated.
Especially in automated systems that use motion.
Right.
As previously mentioned, the microscope objective's resolution is finer with higher NA. As you can see, the numerical aperture in the formula here is in the denominator, so as the numerical aperture gets larger, the resolution gets finer. What you can also see from the formula is that the resolution is dependent linearly on the wavelength. So therefore, lower wavelength, i.e. more blue light, will yield a higher resolution than red light or near infrared light. For example, if you have a wavelength of 550 nanometers and a numerical aperture of 0.75, which is a pretty standard 20x microscope objective for fluorescence, your resultant resolution will be on the order of a half a micron. Another consequence of the numerical aperture is that it directly affects something called the depth of field. So as you would expect, when there is a plane where the microscope objective is in perfect focus. However, there's a region on either side of that plane that will yield a essentially perfect or indistinguishable from perfect image quality. However, the depth of field is inverse, as you can see in the formula, to the square of the numerical aperture, meaning that there's a pretty high dependence on the numerical aperture. If we take two extreme cases, the 10x microscope objective, 0.3 NA at 500 nanometers will yield a 6.4 micron depth of field. However, a 100x magnification objective with a 1.47 NA will yield a depth of field of 0.16 microns at that same wavelength.
And as the depth of field gets finer and finer, it's increasingly important you have a very good focusing stage, and we'll be touching on that later. It's important to distinguish between low and high throughput microscopy. Low throughput microscopy is typically associated with academic research. The microscope is typically a commercial off-the-shelf model, and perhaps a few key images are taken over the course of the research, and finally a paper is published. But we're really talking about enabling something very, very different, which is high throughput automated microscopy. If we're going to do that, we require very fast imaging speed, very fast motion, and a lot of light. And typically, this is performed not on a commercial off-the-shelf microscope, but on a bespoke OEM microscope that does no more than is needed. A bespoke microscope is the exact opposite of the Swiss Army knife that traditional commercial off-the-shelf microscopes are, and it is really designed to do one thing and to do one thing really well.
There are a number of reasons why you'd want to build a custom microscope. The primary reason that most clients would like a custom microscope is that they'd like to achieve higher performance, whatever that means for their particular application. That might be signal to noise, sensitivity, resolution, field of view, or throughput, or something else. Another reason might be to miniaturize, whether it's for size reduction or weight reduction, so that it can be easily integrated into your instrument. Lowering costs in production is always desirable. Yet another reason to design a custom microscope would be to tightly integrate the motion and optics to achieve that very high throughput that Kevin and I have been speaking about throughout this presentation. Or to incorporate novel or specialized optical modalities that would be specific to your technology, or to enable simultaneous imaging modalities like fluorescence and white light. And when I say white light in quotes, what I mean is that it might be a different color than the emitted fluorescence, but essentially running in transmitted or bright field mode. It would also be to enable multi-channel, i.e. multiple fluorophores being imaged at the same time, or hyperspectral imaging where you have many components of the spectrum being imaged simultaneously. Another design goal might be to enable volumetric imaging, which allows a three-dimensional imaging of thick samples. And finally, any system that would be developed custom has the potential to develop protectable intellectual property for the customer.
One of the points that Steve mentioned there was to tightly integrate the motion and the optics. And in fact, that's something we work together very closely on. And we have an example here where a very significant contrast between a commercial off-the-shelf microscope and a bespoke microscope, where the system on the right is actually about the same size as the camera of the system on the left. And we'll be talking a little bit more about that particular system later in the webinar. The technique of fluorescence microscopy depends upon the fact that when you stimulate certain compounds, their electrons are raised to a higher energy state. And when they decay, they emit light. And because you don't get quite as much out as you put in, the light is always redder, that is to say, of longer wavelength. We happen to have an example here of some fluorescent minerals, green, pink there, and yellow. And these are macro examples of fluorescence. For those of a certain age, you might remember black lights and Jimi Hendrix posters. But in fluorescence microscopy, the fluorophores are quite a different thing altogether. For the case of the pinkish red mineral we just looked at, given that the light source was 365 nanometers, we have nearly 300 nanometer difference between the excitation and the emission. For biological samples, this spread, this difference, which is referred to as the Stokes shift, is often a lot smaller, on the order of perhaps 30 to 80 nanometers.
In fluorescence microscopy, we're not going to be looking at Kevin's minerals. Typically, the target of interest would be attached to a molecular probe called a fluorophore. This technique has enabled multiple applications. For example, the most common or a primary one these days is DNA sequencing, but also many diagnostics run off of fluorescent microscopy. Below is a representation of a typical fluorescence microscopy system, whereby you have excitation light coming in, maybe from an LED, which is narrowed down by an excitation filter, and then is reflected off of a dichroic mirror down through the objective onto the sample. In this case, the sample might be in Texas red, where we'd have 586 nanometer light coming in from an LED to excite Texas red. The fluorescence emitted by the sample is collected by the objective lens and is passed through the dichroic and onto an emission filter, whose main purpose is to remove any scattered excitation light. That remaining red shifted light, or fluorescence, is focused by the tube lens onto the image sensor for detection. Despite the power of fluorescence microscopy, it does come with some significant challenges. For example, signals are typically 10 to the 6th to 10 to the 9th power lower than the excitation energy. I often liken this to trying to see the signal from a flashlight shown upon the sun. This means that high illumination powers are usually required. However, even with higher illumination powers, the signals are generally near the noise floor of current imaging sensors. And if you try to overcome that limitation by integrating for a long time, you run into the problem that fluorophores often photobleach, that is, stop fluorescing if you have extended exposure times upon them. Another problem is that other molecules in the sample might fluoresce, particularly under UV or blue excitation. All the filters in the system must be very carefully matched to the light source, whether it be an LED, a laser, or a white light source, such as an arc lamp, and also to other fluorophores that you might want to detect or that might be nearby that you don't want to detect. And you also have to maximize the signal while avoiding crosstalk between the excitation filter and the emission filter. Another problem is that nonspecific biochemistry is also a frequent issue. Fortunately, that's not generally my job to handle. Having designed microscopy systems for fluorescence for decades, here is the list of the design errors that I frequently see when going into a new program. Number one is the assumption that a 10x objective needs to be used at a 10x or a 20x, whatever the number might be printed on the side, when in actuality, you can adjust the actual magnification of the system by adjusting the focal length of the tube lens. This turns out to be a very powerful tool. For example, one of the reasons why you might want to change the focal length of the tube lens is to change the total magnification of the system to allow the use of an objective with a much higher NA. By using a much higher NA objective, you can increase the light both to and from the sample. Fluence to the sample scales as the NA squared, but so does the light collection from the sample. So fluence at the sensor scales as Na to the fourth. Basically, if you double the Na, the fluence goes up 16-fold. In a recent application, we had a target magnification of 2x. However, by using a high Na 10x objective with a tube lens focal length 1/5 of the standard, we were able to increase the sensor fluence by over 500x, or 625x to be exact. However, it should be noted that the price you pay for this massive increase in fluence is a smaller depth of field and a smaller field of view. Another mistake that I frequently encounter is trying to violate optical étendue, which is a law of physics that states that the product of the Na, or the cone angle, that and the area being imaged or passed through the objective from the illumination side is fixed by the objective's capabilities. Frequently, clients will ask me, why don't we just put 30 LEDs into the system and get a lot of light through the system? But that's not possible because you'd only be using a very small fraction of 30 LEDs rather than all the intensity from one LED. And it's almost always beneficial to use all the intensity from one LED because of the lack of extraneous heat generation and power requirements.
Back in the day, I would routinely ask Steve to violate étendue. I'd find these really high power, large LEDs. And I have to say he was quite high church about it and refused to violate étendue under any circumstance.
A third mistake that I frequently see is insufficient or excessive pixel resolution. With insufficient pixel resolution, you won't be able to resolve features on your object as well as you could in a well-matched system. With excessive pixel resolution, it slows down your readout, and it's really pointless to have more resolution than you need. Another mistake that I frequently see is not matching fluorophores to available light sources. A lot of times it turns out to be an iterative process where I work closely with a customer to get the fluorophore to match a specific light source like an LED or a laser. And you really want to match that to maximize your signals.
Another issue is not matching the optical throughput with the motion. In particular, during the motion from one field to the next in sequential field imaging, we want to make sure that the image download takes no longer. In essence, if we can move from field to field faster than you can download the image, you need a faster camera.
Another issue that I frequently encounter are too many optical adjustments in the system. But I'd like to say you want to have no more than necessary and no less than necessary. Kevin has an adage on that.
I say in many cases, the capacity for adjustment all too often leads to the likelihood of misadjustment.
Or alternatively, in the real world, we call that using hard stops and tighter tolerances and not spending time twiddling knobs while adjusting a system. Another common mistake is maximizing the Na, or light collection efficiency, of the system without considering the effects on the depth of field. In a system where you've maximized the Na, your depth of field will be very shallow, and although on paper that will look like a great system with very high collection efficiency and very high resolution, if your sample isn't of the utmost flatness or coplanarity with the objective, then you can run into issues of defocused sections whereby your overall system performance will be lower than it would be had you designed with a lower Na, therefore a higher depth of field. Another one that I commonly run into is that the client at the first meeting will say, we don't care, let's just get a really expensive scientific CMOS camera in the system, and that will solve our signal to noise problems, when in fact that very rarely solves the signal to noise problems. If your integration time is less than 3 seconds, it's unlikely that a scientific CMOS camera will solve anything, and you can use some of the very good Sony cameras that have been coming out lately.
Yeah, in particular, dramatic savings are possible if you investigate Sony's newest generation of backside illuminated CMOS sensors. They're getting remarkably close to scientific CMOS and can be less than 1/10 the price.
That's right. Next on the list is the failure to consider the angle of incidence on the fluorescence filters in the system. Even in infinity space, a fluorescence filter is only designed to accept a range typically on the order of plus or minus 4 degrees. And if you have very wide optics that have very fast optics that allow much larger field angles through the fluorescence filter, the fluorescence filter will actually shift in wavelength, and you start getting crosstalk between your excitation filter and your emission filter. And what this means is that excitation light, which you remember is 10 to the 6th to 10 to the 9th times brighter than your emission light, a portion of that will start leaking into your image. And it doesn't take much of that much power to override or swamp your image. And to our last point, almost all commercial off-the-shelf microscopy systems from the big vendors are based on color illumination, which is a vestige of when filament bulbs were used as illumination sources. However, it should not be assumed that color illumination will always give the highest uniformity or highest brightness overall of an image in the system. Frequently, a well-designed critical illumination system can outperform a color illumination system.
In automated fluorescence microscopy, the total imaging time for the entire sample can be quite long, and it's of critical importance that the sample remain in critical focus throughout that entire period, irrespective of whether it is perfectly flat. As a result, there has to be a Z stage, which typically will focus the objective, and there also has to be an autofocus strategy to inform that Z stage. Now, at the moment, the most popular technique for focusing uses lever-amplified piezo-flexure stages, but these have a number of problems, and we have white papers that go into this. Dover Motion's award-winning DOF5 is a direct drive stage with built-in counterbalance and complete drive and control built in, typically with 5 nanometer resolution, which is well below the depth of field of even the highest NA objectives. Again, though, there has to be a way to tell the DOF5 where to focus, and this is the function of an autofocus system. In some cases, this is done by what's called contrast-based autofocus, which involves taking a series of images through the vertical space and deciding which one is the sharpest and using that. But that's very time-consuming. More efficient is to use continuous tracking laser autofocus from suppliers such as WDI. And there's also an interesting strategy for some transmissive samples of using a pair of LEDs and processing a single image with a lot of math to determine the distance to proper focus.
As an example of a case study, this is a compact fluorescence microscope, fully functional with XYZ motion, that was a collaboration between a client and BioDevice and Dover Motion. In this figure, you can see some of the optical elements. For example, in the middle, it looks tan with a little yellow line on it. That is a standard microscope objective, high NA, but standard microscope objective. And I'll follow the light through the system to explain how the optics are laid out. So down at the bottom, you can see a heat sink, and to that heat sink is mounted a very high power LED. However, LEDs are very good light sources because they're very bright and relatively monochromatic, not quite monochromatic, but relatively narrow band of output wavelengths. But they do still have structure that you couldn't use to image the LED at the sample plane, because all the structure that is at the LED would end up in every image. So we use an intermediary integrating rod, which is a glass rod that is designed such that it gives the right field of view through the objective and maximizes the light coming out of the LED into the field of view. The light is collected by that microscope objective facing upward up near the top, and it travels back down through a dichroic to a board level camera that's mounted down at the bottom. However, what's interesting is that we've integrated the motion, and I'll let Kevin speak to the motion part of this.
Sure, Steve. So in this case, the fluorescence microscope was going into a place that was extremely space constrained. In fact, it was going into a place in an instrument where there just happened to be some space we might be able to live in. The instrument had not been designed with this in mind. And as a result, very, very tight and demanding space constraints, which is a specialty here at Dover Motion. So the XY stage actually wraps around the objective and the optical axis. And the objective is being moved by the Z axis, which is actually mounted to Steve's illumination system. An interesting feature of the XY design is that there are no moving cables. It's a 3-axis system with no moving cables. The motor coils are all stationary. It's a moving magnet in all three axes. But interestingly, the optical encoders, the glass scales are moving, but the readouts, which have cables associated with them, are all stationary. And the way we did that for the XY stage is that we actually have a two-dimensional encoder. So the whole thing ended up being sort of, you could hold it in the palm of your hand, very high performance. And this took advantage of the modified focal length tube lens that was mentioned earlier, and as a result, developed enormously higher fluence at the sensor than would otherwise have been the case. And in fluorescence microscopy, fluence at the sensor is critical. Before we jump to the Q&A session, I wanted to point out that we have some collateral material, which everyone who's registered will be able to access via links in the slide deck that we're going to send you. One is a white paper that's quite recent on optimizing motion for sequential field imaging. It's pretty key. There's another white paper on basics of image sensors, talking about pixels and their attributes. We also have a microscopy calculator, which it's in MathCAD, but it'd be easy enough to put it in Excel. And this is where certain elements of the system design are entered, and then it calculates for you the depth of field, the resolution, the degree of oversampling, etc. And then finally, we have an imaging throughput calculator that directly contrasts sequential field imaging with TDI scanning imaging and allows you to determine which is the optimum choice for any given application. Certain work that we've done here at Dover Motion on dramatically reducing move and settle times is actually tilting the balance these days away from TDI and towards sequential field imaging. That calculator is available, and the link will be in the deck. We're going to review questions that came in through the chat session and be back in just a moment.
Okay, so looks like we got a question. When would you use color illumination versus critical illumination? And you would use color illumination certainly if you had a very non-uniform light source like a halogen lamp bulb, which is why it was used or is used in most modern commercial microscopes. However, you would the problem with color illumination is that going through the objective, you get a cosine to the fourth effect. So once again, there's that fourth power. And what it means is that you get very non-uniform illumination with very high NA objectives. So very high NA objectives with trying to use the whole field of the objective, your corners will be dimmer than your edges. Critical illumination avoids most of that, and you can design, or I can design, a critical illumination system that would give very high uniformity. But another benefit of critical illumination is that it gives very sharp cutoffs. So if you're illuminating a square area, that just the square would be illuminated, and outside of that is not illuminated. And where that comes in value is that you would have very little photo bleaching outside of your field of view.
Now, there's a downside to critical illumination you have to be careful about, and that is that the surface that is illuminated in the field of view is the end of that integrating rod. And if you get dust on the rod, that'll show up.
That's right.
So you have to really arrange for some seals and make sure it's clean when you assemble it.
And generally in systems that we've designed previously, the first lens after the integrating rod is in a sealed chamber along with the other end of the integrating rod, and that prevents any dust from getting in there. Did you want to get the second question?
Yeah. When do you use sequential field imaging versus TDI imaging? That's a complex trade-off. Generally speaking, with more economical light sources like LEDs, you're typically going to be better off with sequential field imaging. In TDI, it's very important to hit it with a lot of light. That's right. So if you have a big budget and you can afford lasers, especially at multiple wavelengths that can add up pretty fast, then that can be superior. But what really matters is how many square millimeters you can image in a given amount of time. And one of the key variables there is how long it takes you to move from field to field, which is also the time that you move, that you're going to download the image. And so if you can get that really compressed, then in fact, there are a number of cases where sequential field imaging is more efficient than TDI. So it really depends upon the specifics of the application. But as previously mentioned, we have spreadsheets that would help you understand that.
And to just expound upon what Kevin was saying, I've designed both TDI-based systems and SFI-based systems. And the SFI system with a LED, the LED source, the light source, typically costs about $20 for 2 watts of power. And for a TDI system that requires a laser, you end up having to use a laser that has 5 watts. So it's not a lot more power, but costs on the order of $10,000 to $30,000. So there is a big difference there.
We once designed, in conjunction with George Church at Harvard, a 4-color system with 4 1-watt lasers, and the price tag on just that light source system, the 4 light sources, was $125,000. Let's see, we're beginning to get the Oscar music queued up. I'm told we're running a little late. We do have some additional questions, and we'll get back to the submitters by email. I'd like to thank you all for attending, and if you have any questions, please reach out.
Thank you.